I'm Dr. J.D. Strong. I'm the Maui Technology Education and Outreach Specialist, and welcome to the University of Hawaii's Pukalani Advanced Technology Research Center. Part of my job is to invite speakers to talk, and we're really fortunate to get Tom Schad here. Dr. Schad is, well, he grew up in a small cattle ranch in Texas. Got his bachelor's degree at Notre Dame, went to the University of Arizona, where he got his PhD in solar physics, studying the evolution of magnetic fields in the solar atmosphere, and so that meant a lot of spectral polarimetry and all sorts of fun things like that. And that then brought him to the University of Hawaii. He was hired by the Institute for Astronomy to work on a first light instrument for the Daniel K. Inouye Solar Telescope, which is being built at the summit of Haleakala. And once he got here, he married the love of his life, and he's here to hear that. Yes, and yes, and their new addition to the family. Then he was offered a job by the National Observatory, and he took that position. And we're fortunate that he's still in the same building. I don't even think he changed offices, so we're very lucky to still have him with us, and they're lucky to have him. So let's give a warm welcome to Dr. Tom Schad. All right.
All right. Good. Thanks, JD, and thanks everyone for coming and joining us on a Friday evening to talk a little bit about science. It's a really fun thing that we get to do occasionally here. So please welcome, and let's settle in, have a little fun, talk a little bit about the sun tonight. Thank Stefan and all of the IFA people who do such a good job at putting this together and also broadcasting us over the internet. Stefan is broadcasting us live now, and people can go back to these videos in the future and review them if they want. So tonight the topic I chose was solar rain, coronal rain. This is a topic that's near and dear to my heart because I did part of my dissertation on it, but only a very minute part of that, and that's actually measuring the magnetic field in what we call solar rain, which means I'm an expert at a little piece of it, but not everything. And in a talk like this, I take my little piece of knowledge, I try to expand it to the bigger broad thing, and then I try to connect it to something real, which means I don't know. It's that classic PhD problem of, in graduate school you learn more and more about less and less until you know absolutely everything about nothing. So as I venture on here, if anything you see, you say, oh, that's wrong, let me know, please. But so coronal rain is something that I studied as part of my dissertation. I'm still studying it now, but it's also a topic that I chose to talk about this time because a few weeks ago, JD asked me what I wanted to talk about, and Tropical Storm Darby was going through, and I said, well, there's all this rain outside. Let's talk about rain. So, and then very James Taylor-esque. This picture, what you're seeing right now, is a movie from the NASA Solar Dynamics Observatory. What you're looking at is helium gas that's about 50,000 degrees in temperature. And you're looking at the limb of the sun, the edge of the sun. Remember, the sun is about 110 Earths across, so this thing is huge. So what you're looking at here is height of Earth. And what you're seeing is a big rainstorm or something, or some equivalent on the limb of the sun. So roughly, the of each one of these things is about 1,000 kilometers. So this is a very big image, and this is a small piece of the image of the full sun. Like I said, we're looking at about 1,000 degrees in temperature, but actually all of this external stuff around here is in millions of degrees temperature. So it's actually really cold material in an otherwise hot environment. And this is what we see. We call it rain just because it forms up there and it falls down like rain. Now, rain is not like rain on Earth. I mean, it has some certain characteristics that are similar, but then there's some weird things about it. Let me get this movie going. So on the left we see a rain cloud on the Earth, and on the right we see some rain happening on the limb of the sun again. This time you're looking at a silicon-4 gas. Actually, I apologize. This is magnesium-2. So this is a magnesium atom that's been ionized once. One electron has been taken off of it, and you're looking at it. And it's in about the 20,000 degree range. And what you can see on the left is rain, which is, kind of regular Earth temperatures, and you're seeing something here, 20,000 degrees. And then kind of out of nowhere, at some point, things start to form, and then you see this stuff falling out of the sky. So if we look at some comparisons here, first of all, rain on Earth is falling from clouds. Rain on the sun is kind of out of nowhere. You don't necessarily see a cloud form, you see rain. Rather, you see something form and immediately fall. On the left, you see on Earth, it's falling directly towards the Earth, towards the ground. On the sun, it's falling. It's not going straight down, it's falling along something. On the left, you see rain speeds are about 5 to 20 miles per hour. The bigger the raindrop, the faster the rain falls, because it lowers the drag coefficient on rain as it comes down. On the right, if I remind my numbers, you're seeing speeds of 100,000 to 500,000 miles per hour. So this stuff is very fast. This whole movie is probably about an hour and a half of real time. And it's a big movie again. This is 10 Earths tall. So this is some 0.01% of the speed of light. This is very, very fast material. On the left, again, air and rain, those temperatures are not all that different. You can be in a cold rain, and the rain can feel cold to you, but really the temperatures are not that stark. Tens of degrees, maybe in the upper atmosphere a little larger than that. But again, the temperature differences in the corona are very different. What you're seeing falling out here, there, is tens of thousands of degrees, but this black stuff that you don't see is actually 1 to 2 million degrees. So this is all weird stuff. So the rain is forming, but it doesn't have clouds, but clouds do exist on the sun. The sun actually from about 12 hours ago or so, taken from one of our telescopes that the National Solar Observatory runs in Big Bear, California, on the Big Bear Lake. And what it's showing you is a hydrogen. So you're looking at hydrogen gas formed in the kind of middle atmosphere of the sun. You can see that the sun is not just a blank disk, but rather there's stuff on it. For example, this dark spot here is a sunspot. Sunspot being a very strong concentration of magnetic field. There's other bright regions and things, but then you can also see these big dark lines here, 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 and here. And you can also see this stuff coming off of the edge of the sun that's bright. These are the clouds of the sun. When it's on the edge of the sun, we call it a prominence. And when it's on the disk of the sun, we call it a filament. And we've known that these existed for a long time. And they're the clouds of the sun, but they're really different than clouds on Earth. So here's a little movie of a cloud from another spacecraft, a Japanese spacecraft, showing one of the clouds above the limb of the sun. You can see that it's really tall and suspended. It kind of floats there and moves, but it has turbulent patterns. These things also get really interesting because they affect us. And this movie shows again the SDO image of a prominence lifting off, exploding out into the interplanetary space, and then you can see some stuff coming out behind it, and that's also coronal rain. Basically, anything falling to the sun is rain. However, this big mass of plasma at 50,000 degrees and at speeds of a couple 100,000 miles per hour sometimes comes directly at us and hits us. And in fact, if I go back to this movie, I didn't plan to do this, but if you go back to this movie here, you saw that little spray of white specks early in. That's exactly the environment of space that's affecting the camera in space. So the high energy particles that the sun is producing comes at our cameras and routinely affects our electronics. So this stuff has been around for a while. And this I find to be an amazing image. So Father Pietro Angelo Secchi, who was an Italian astronomer back in the 19th. He was a fundamentalist, and he was the one who developed the technique that you could look at the sun in a particular line or a particular spectrum point. He created something called a spectrohelioscope, and what he created was a way of observing hydrogen gas by itself in the sun, but he didn't have a camera or photography. This was all bare eye. So what he did was he was a very good artist also. So he drew everything that he saw. So those same beautiful movies that we're seeing with cameras, he saw bare eye, and then he drew this. And it's amazing that he drew this in 1871, and yet it's very similar to the stuff that we're seeing now, right? Of course, he had absolutely no idea what this stuff was. And in fact, there was a huge debate for a longest time about whether this stuff was on the moon or if it was on the sun, because the only time you saw this type of material, prominences and things, was whenever a moon went over the sun so that you could see it in the background, right? And you would think that, okay, the moon is on top of it. Is it part of the moon or the sun? Well, Angelo Secchi, because he created this new technique, obviously he said it's from the sun right away, because he didn't need to have the moon in front of him to see him. So today it's kind of, we have a couple questions we want to ask ourselves, and that's kind of informed in the atmosphere. We want to kind of understand that tonight. And we also want to use it for something. And for us, as solar astronomers, we're really interested in understanding the energetics of the sun. And I think rain has a lot to tell us about exactly the corona gets to this crazy 2 million degree state, which is so very different than what you might think otherwise. So to do this, I kind of want to do a comparison of Earth and the sun again. Let's focus a little bit on the differences of the structure of Earth and the sun. And again, I want to encourage you, if I'm going too fast, or if you have a question or a clarification or a point to make, just raise your hand or speak up, and please do so. Yep. He had a telescope, but he was looking. So in those days, you wouldn't look bare eye at the sun, but you would often project the image. And in fact, I don't know exactly what he did for this instrument, but back the old drawings, you would project the image of the sun on a piece of paper or on a wall, and then you would look at the reflected backlight from that. So it was still safe. Yeah. So if you get into the specifics. Oh, thanks, JD. JD reminded that I should repeat the question. So the question, if you didn't hear, was about the safety of looking at the sun, or how you looked at the sun, whether it was with your bare eye or not. So if we look at the structure of Earth's atmosphere in terms of temperature versus height, this is what it looks like. And this is the best graphic I could get, unfortunately, even though it really gives you the full atmosphere. But concentrate just on this lower part where we have the troposphere. Look at the temperature versus height. So temperature is here on the bottom axis, and this is height. You can see that down here in the troposphere, we have a very strong decrease in the temperature as you go high. This is understood, right, as anytime you go to Haleakala or any mountain summit, you're colder, right? This is the very familiar for most of us. And this of the Earth is being influenced by a sun's radiation that's coming down from below. This is very, very different than what we have in the sun. And I apologize for this graphic. You have to turn your head, everyone. But we have the same thing. This is temperature on the bottom. This is 1,000 degrees. This is 1 million degrees. This line here is that down at low heights we have about 6,000 degrees, or 5,000 degrees on average. If you get up into the middle heights, you get 10,000, and then all of a sudden, and this is, you go from 10,000 degrees all of a sudden to 1 million. Now, if we think about rain and where it forms, it's really different for the sun and the Earth. So on the Earth, rain primarily forms here at the top of this increase of temperature, right at the tropopause. For the sun, the rain here, way up in the hot corona. These are very, very different environments. What this isn't showing you is what causes more to this, but it doesn't show you is that there's a magnetic field on the sun that's some 1,000 times stronger than what we have here on Earth. So if we look at rain on Earth, I had to go back basically to my 8th grade physical science textbook because I couldn't quite remember. I mean, everybody learns the water cycle, right? But it turns out the water cycle is not completely well known. I mean, we know what the water cycle is, but it actually is intense debate how rain forms in the Earth. Actually, how you get from a minuscule piece of water that condenses out of the atmosphere into a raindrop is a thing to do. Anyway, the water on Earth is well known. We have many key stages here. One, we know that we need evaporation of water. So a key ingredient to rain on the Earth is water that evaporates. Another thing with rain, you might not think of it, but a very essential piece of rain is that you have a lift, right? Rain falls from somewhere, so you have to get it from the bottom to up. So there's a lift. And then lifted, there's also a condensation point forming a cloud. And then as that condensation happens, then you need to form rain particles, and those precipitate out of the atmosphere. So why do clouds form where they form in the Earth? Well, it turns out it has everything to do with that temperature structure. It has everything to do with how the dew point temperature changes as a function of height. So this graph is kind of showing you temperatures and dew points and relative humidity in different ways. So the dew point, just to remind you, a dew point is the temperature at which a certain concentration of water in the air will form a condensated, will start to form dew. So anytime you hear the weather report, the dew point, if the temperature gets down to that dew point for that day, you know that there might be a ground fog layer or there might be some dew forming. Well, the dew point is dependent on many things, and one thing it's dependent upon. Well, how do I show this here? So what this shows is here's the air temperature. If the air is this temperature, and the dew point is this temperature. Sorry. Can you hear me? Having technical difficulties. Can you hear me now? No, it's not working. Stay tuned. Testing. 1, 2. Testing. You got it. Okay. All right, we're good to go. So back to this graph. We have air temperature down here, dew point here. And what these lines show you is different humidity levels. So if, for example, the temperature is 70 degrees and the dew point is 70, then you need 100% humidity. Right. That's what this is kind of showing you. The dew point is 70 and the air temperature is 70. Then this black line tells you that the humidity is 100%. The dew is forming. Right. That's the condensation. That's when condensation happens. Starts to happen. But so this is an example of how these various parameters depend on each other. But the point is, it's actually a little bit more complicated. So the temperature, the air temperature, and this relative humidity level is also dependent upon the pressure in the atmosphere and the density in the atmosphere. So if you instead if you go through the calculations and you determine how the dew point and how the temperature of the air reacts as a function of height, you get something like this. So if you take that troposphere that we were looking at and we blow it up, this is forget what they call this. There's a name for this type of chart. But what you have on the bottom is temperature, and you have height, and then you have a couple curves. What these curves represent is what happens if you take a parcel of gas and you move it. So say you take a parcel of gas here that's dry, or have some small amount of water in it. If you take that gas and you lift it up, this tells you what the temperature change is as you lift that up. So because the pressure is dropping off, actually you get that parcel of gas expands, just like a balloon, right? So as it expands in the atmosphere, it cools. So this curve tells you that if you move up 2,000 feet, you cool off 5 degrees. This curve here tells you what the dew point is doing. So how does the dew point change for that same piece of gas with height? Down below here, say you're at 0. You have a thing of gas that's at 20 degrees, but your dew point is at 12 degrees. You're not forming any condensation. You're not forming clouds. But now let's lift that up to 3,000. All of a sudden, you're at a point where the temperature of that gas parcel that you've lifted is all of a sudden the same temperature as the dew point. So as you move it up, it becomes easier and easier and easier to cool and condense. This condensation level happens to be up at the edge of the tropopause, exactly where our clouds form most of the time. So there's power in this lift. This is where the magic of rain happens, right? And we know this if we watch the weather report, the big weather cycles going on in the country and the world, how these different patterns emerge about how rain forms. Rain is tied to clouds on the earth, and those clouds are tied to oftentimes this lift. You need to lift the material in order to get a cloud to form. And there's a couple ways to do it. One way is if you're out in the desert and there's a little bit of humidity in the air, but the sun is warming the air, you can build up convection. You can build up a thunderstorm in the middle of the Midwest or in Arizona. Another way is if you have a cyclone of some sort, hurricane, tornado, something that merges up and pushes the air up. A very common one, mainland especially, and occasionally here, is when a front comes in, you have cold air coming in, and it takes that warm air and it pushes it up. And as it pushes it up, the dew point goes down and you get condensation. But the one we're most familiar with here on Maui is the orthographic case, when you have cool trade winds coming in from one direction that pushes that water up the mountain to a lower dew point and creates clouds. So we see this all the time right on Maui. I mean, this is the story of Haleakala. Unfortunately, that's Haleakala. That's the West Maui's. So, grain of salt. This is the classic trend, right? Trade winds come up. You have the wet side on one. That same thing happens on Io Valley. As the wind is coming up, you get the clouds formed. But as they form, they release energy with the rain, which there isn't much on this day. But then by the time it's past, it's already cooled, and it can no longer form the clouds as it gets across the peak. Yeah. So this explains, of course, this orthographic, this lift explains rains for us, and explains why we have wet areas of the very similar process actually happens on Titan, the moon Titan, which is orbiting around Saturn. So we know this because actually we had the Cassini mission, a NASA mission that flew to Saturn, and it had, if maybe some people remember the Cassini mission and remember there was something called the Huygens probe. And the Huygens probe actually launched off the Cassini spacecraft, and it fell through and landed on the surface of Titan. It was actually planned on just in case there was a water surface on Titan, it could actually do a water landing. It landed in a dry spot, actually. But one of the key things it measured was actually this profile, this temperature versus height, this pressure versus height profile. So we know what that is on Titan. And this is sort of what happens in Titan. Of course, Titan is way out by Saturn, and there's not as much sun. So it's a very cold place, and in fact, it's so cold that water can't evaporate. Water can't evaporate. You can't get condensation. You can't get clouds. You can't get rain in water. But you can evaporate methane. So the surface of Titan has a lot of frozen methane that can sublimate and evaporate into the atmosphere. And the exact same thing happens. The methane goes up that curve, lifts up, it forms clouds, and we can observe these clouds and measure those clouds from Mauna Kea. Actually, we've seen the clouds of Titan using Keck. And those clouds rain out methane, and they create lakes. So this is the northern latitudes of Titan, and you can see these lakes of methane gas, of liquid on the surface. Absolutely. So it's an important component, actually, the greenhouse effect on Titan, because that greenhouse effect is what boosts the temperature high enough so that this process can go on. Without the greenhouse effect, it would be a little too cold. Of course, same reason we have a greenhouse effect even before that was important for us. So that's all Earth. That's stuff. So this is from Hinode, that Japanese spacecraft from 2006. You're looking at the calcium line at this time, and what you see is a lot of crazy stuff happening. You see a sunspot. You see what we call the forest of spicules, these big long things that are waving back and forth. This background stuff here is a prominence. It's one of those clouds on the sun. But then this stuff that's kind of coming out of nowhere, that's really fine but tall, this is that rain again. So we've learned a lot about the Earth's rain and Titan's rain, but can we really apply that here? Sure. Right. So we'll get a little to this. The magnetic field makes all the difference in the sun. The magnetic field. So it's really the topology of the magnetic field, how the magnetic field is shaped, that really dictates a lot of this behavior. But most of the images that I showed, like this image, is in a very specific piece of the spectrum of the light that we look at in calcium. And what you see is mostly all the same temperature. However, that's not to say that there's not other temperatures going on in this area. So there's other structures that you're not seeing, right? And that's actually my next point. So first, we have a clue already as to what rain is in the sun. We've already told you one, and that is the fact that it's cold. Cold in a hot environment. So something has cooled this material, and that is key in the process. So keep that in mind. But to the point of not being able to see things, but things happening on the sun, this is a look at what's happening during the evolution of a rainstorm on the sun. But this one is actually on the disk of the sun. I'm actually not showing you on the side of the sun. I'm showing you right kind of in the center of the sun. And this is a big region. There's actually a sunspot there. So my thumb is about the size of Earth. Big. And what you can see is, as this goes on, there's something that happens right here. All of a sudden, something appears out of nowhere, right? And all of this stuff kind of appears out of nowhere. That's not to say that it wasn't there before that. What's happening is that material is cooling. So before you see it, like right now, it's after this crazy thing goes away, this is kind of a dark area. As soon as it comes up, boom, what you're seeing is that that material has cooled that you can see it in that light. So this is which light is this? This is 171 angstrom. I forget. I think this is iron 10 or something. So very ionized gas. So all of the, like those other images that I showed you where the gas was all 20,000 degrees or something, the gas that you're seeing here, anything that's bright, is about 1.2 million degrees. So, but this is an interesting case because that those loops kind of appear out of nowhere, but actually there's rain here, but you have to look really hard to find it. So let it evolve. So this thing shows up, but then it turns dark at some point, and you can see stuff moving this way. Yeah. Very good question. Very, very, very good question. So the question was my next slide, actually. So you're way ahead of me. So we're trying to understand this rain, but the question was a very good one, and one that we've been dealing with now in solar physics for 60, 70 years. That is how odd it is, the fact that the upper atmosphere of the sun is so hot. Any other environment that we've ever been to, Titan, Earth, Jupiter, any other planetary environment, the surface is always cool, or is always warmer than those higher heights. Yeah, once you get way above the Earth, then the temperature is a little different, like I showed you there in those early profiles. But that intuition that you go up to the Haleakala and it's colder, that doesn't work on the sun. So there's something else going on the sun that allows the temperature to change and get so hot higher up. And radiation doesn't do it. Thermodynamics doesn't do it. We think a magnetic field might do it. And the energy related with the magnetic field. So this is, again, that profile of what the solar atmosphere looks like. So this is height. So this is lower heights. This is higher heights. This is temperature on the left. So that's 10,000 degrees, 100,000 degrees, and 1 million degrees. And you can see that heights down here, there's not a scale here. This is about 2,000 kilometers. You start at about 10,000 degrees, and then you go up. And over a few hundred kilometers, you spike way up. And all of a sudden, you're 2 million degrees again, or hotter. This is really hard to explain. We know it has to do with the magnetic field. We know it has something to do with the fact that the sun is always churning. So there's the photosphere, the surface of the sun, is always churning like a boiling pot of water. And that churning can actually shake those magnetic fields in a way and give those magnetic fields energy that can then go up into the corona. But the processes that actually explain how that energy goes from that shaking to the higher corona is really, really difficult. There's about 15 different ways that you can do it, and they all give you the same temperature, and everybody argues, and you'll see 3 articles a year in the newspaper that says somebody has solved the coronal heating problem, and they're all wrong. It's been around for a long time, and it's going to be around for a while, because those energy dissipation scales are very tiny. But that's where coronal rain comes in, too, because it helps us understand it a little bit. So when you're talking about energy in the atmosphere, there's really kind of 3 main terms of energy in the sun. And to get some handle about what solar coronal rain is, we have to think about these energy contributors. And they're basically conduction, radiation, and some unknown energy. That unknown energy that we've already talked about, that magnetic field, whatever it is. It's some unknown energy source that derives from the magnetic field, but we don't know what it is, but we don't care right now. It's just X. But these are the main 3 energies, the flows of energy. You can get a flow of energy because of conduction, much like the pot, the handle of a pot gets hot. Especially if a copper pot, your handle conducts heat towards you. So heat conduction happens from a hot surface it flows heat to a cooler area. That's one thing that conduction do. Radiation can cool too, so if things give you light, that light carries away energy, and that energy can actually be substantial. The sun is giving out 10 to the 26 ergs a second or something like that. That watts. Somebody check me on that number. And then there's this other flux, this energy. So to understand rain on the sun, we have to think about how these three things work in congruous with something that looks like this. So to do this, I'm going to try to work through the model of a German guy named Daniel Müller, who has come up with a nice demonstration of how this coronal rain happens. So if you take that curve of the sun, where it's cold and then goes hot, and you think about a loop, like a magnetic field loop, just like the iron filings in a magnetic field form loops, right? These loops exist on the sun. And this is an example of one. This is a model, it's a simulation, it's not real, but basically what it says is there's a loop, and the black areas here is where it's colder, and as you get more and more yellow or orange, it gets hotter. So down in this region, it's tens of thousands of degrees. Up here, it's 1,000,000 degrees, about. So our task is to somehow take something that looks like this and make it rain. So the solution that Dan Mueller has worked on is exactly trading off these energy sources and trying to determine exactly how one relates to the other and how this evolution happens as you generate the system. So one thing that he's done is that, or one thing that we can show is that if you try to heat up this loop, for example, if you put some magnetic field energy and you put it in here, and you let that energy do its work, that energy is inputted in the lower atmosphere where actually there's a high density and pressures are high. What ends up happening is that you heat that material, but it doesn't change temperature very much because down there the densities are so high that radiation is really good at letting some of that energy go. So radiation is letting go of the energy here, but it's also lending to a pressure increase here. And what that does is really important to the story, because as you increase the pressure there, what you have is the loop heats, the density of the whole loop increases. So you're basically lighting a fire down here, and whenever you light that fire, you're filling up this whole loop full of material mass. That mass is the gas that's made of, that the sun is made of. So it's hydrogen and helium mostly, and other stuff. But mostly it's gas. Now, now we need to have this do something. Now we need this to change its state in some way. Okay, so we've essentially done the evaporation part of the rain cycle on Earth. So we've created some vapor. So now we need to get this thing to form some clouds, even though clouds don't exist. So that comes in the form of what's called an instability. Basically, we need something to cool quickly. And what Dan Mueller has found out is that you can do it kind of two different ways. And it has everything to do with how you heat the loop. So one way he found is that if you don't heat the whole thing, but if you only heat down here, then this instability happens. The other thing that he's found is that if all of a sudden if you're heating the whole loop and then you turn down the heat just a little bit, actually it's not just turning down the heat, it's turning down the scale. So if you heat just this part, but then you heat a little less than that part, you can create something that goes unstable. So this is already telling us something. It's telling us where the heating is happening. So this unknown energy source that's heating the corona, all of a sudden we have some constraint on that. We have some information that tells us sort of what's going on in the sun. We don't know everything that's going on about the sun, but this is telling us that if we do this, we might get something to happen in this loop. Well, in fact, what this does is that say what does it say? Too much cooling to do. Yeah. So what happens here is that when these things happen, you have a reduction of heat, but you had a very dense loop that is sitting there radiating. Anytime there's hot gas, it's radiating and it's cooling. And the only way you can keep this stable is if you keep the flame on it. If you turn off the flame, then all of a sudden that radiation is going to let it cool. But we don't want it to cool too fast. You can't turn it off, because if it turns off, then basically what you're doing is you're allowing everything to just float, and you don't form anything. It's just hot gas goes down. So it's a very delicate process. You need to keep it on, and then you need to turn it back just a little bit, or you need to turn it on just the right amount. However, so when the density increases and you do this, what happens is that these radiative losses up here start to create a little small change of temperature. This is a very, up on the top of the loop you have a very small change of temperature. It's exaggerated here, but it's a very small fraction of what the temperature is. Oop. The temperature drops there, but as the temperature drops, it happens in the solar atmosphere that the pressure drops also at that point. Anywhere you have a drop of pressure, you have the capability of an inflow, right? So if if you stop blowing up a balloon and you reduce the pressure, then all of a sudden the balloon goes down and goes Inouye, right? So you drop the pressure, and then all of a sudden you have things that are coming together. So what happens is that up on the top of this crazy loop, you get stuff kind of coming up together on the very top. And what happens then is that you have this extra material up on the top of the loop. And it turns out that, again, because the density is going up now up there, you're getting more and more cooling. And that's back to this term that we looked at. If you look at the radiative loss, how much heat you're losing, that this is the heat that you lose, and it's related to these numbers, which are the densities. So if those numbers go up, then you get more heat loss. So this process is what we have is we have a heated loop that all of a sudden, because of a small fluctuation in the change, you lose the capability of keeping everything hot at once. The temperature drops a little bit. This material flows in. That creates more density, creates more losses. All of a sudden, you can see that it's going to run away. Everything, all of a sudden, temperature continues to drop along with the pressure. Mass keeps coming in, and you get something that's cold. And the density is so large at that point that it's gravitationally unstable, and you can't hold it up in the atmosphere anymore, and that falls down. So you've made something cool, you've made something dense, and you made it exist in a very, very hot environment, and then you have it fall. That's rain on the sun. So that's what this is showing, is basically once that's done, this cool material actually falls down and flows at those high speeds. In fact, another interesting thing about this kind of material is that these models show that as the material goes down, it actually is running into the other gas. So it's building pressure just like a piston in an engine. So the material is trying to go down, but it's running into itself, the other gas that's in the loop, and it's compressing that a little bit. So what ends up happening is that you don't have rain that's falling at the gravitational rate or free fall rate, but rather it's a little slower. So it has its terminal velocity, just like a rain particle on the Earth would. So it's 100,000 miles per hour, but it could be 700,000 miles per hour. Yes. It is. Yes. Yeah. And but that's all caused by the density. As the density goes up, then all of a sudden the radiation is what, because of that density increase, you get more use out of that radiation loss. Yeah. Sure. It's true. I mean, it's this is one model. This is the it's called the catastrophic cooling model. The most popular because it's the easiest to in the phenomena, but could trigger such an instability. And we'll show one thing here in a second: wave modes, entropy wave modes that can compress things in the atmosphere and allow this condension, that cooling and condensation to happen also. Yes, the parameter space here is wide open. There's a lot of things to. This is active research. Yeah. Yes. Right. So this is a great question. The question, if you didn't hear it, was, does this tube, this loop, or this magnetic field really confine to this? Why does this material, as you're flowing down, why can't it just go out of that area? Good but involved question, actually, because if it's hot enough, then if the temperature is hot and you have a lot of ions, so things are ionized, ions, because of their electric charge, follow magnetic fields. So they gyrate around the magnetic field. So the magnetic field creates this asymmetry in the conduction, such that you can get conduction along one way but not the other. And whatever ions are there are restricted to the motion along this loop. However, an interesting thing that starting to work on in the last 3 or 4 years is what happens when it cools. Once it cools, you don't have ions, or you don't have as many ions. Actually, you start to get a lot of neutral material. You get neutral hydrogen, neutral helium. All of these hydrogen alpha images that I showed you of prominences, that's all neutral material. And the question is, how does neutral material feel in a magnetic field? Because the neutrals don't have to have that gyro radius. It doesn't have to treat the magnetic field in that same way. The neutrals can go out of that loop space, exactly what you're talking about. To answer that question, it's about how strong an effect that is. It all depends on how well the neutrals and the ions interact with each other. Because the other way you can couple a neutral to a magnetic field is by coupling those neutrals to ions. The ions are coupled to the magnetic field. They're sitting there gyrating around the magnetic field. But then these neutrals are running into those ions, and they're actually collisionally connected and restrained to flow with the ions. But that's not always the case. Sometimes they do actually slip. We call it, it's just slippage. It's slippage of the field through the neutral. Not exactly. So I'll show you a video where material can flow down both angles. In this model, the simulation is set up that once it picks a direction, it'll pull it along with you. It's really how you treat the boundary condition here. But it is true also that as this material goes along and compresses here, there's some theories that talk about a negative pressure behind the flow that can then pull up material on the other way. So sometimes you'll see rain coming down these loops, and then all of a sudden you'll see something going up. And why does it go up? Well, it has to be some negative pressure that's pulling it up. And one way you can do that is if you have that material getting that pressure. It's a siphon at that level. Yep. So, the magnetic velocity or the rain velocity? That is a great question. And 2 slides from now, I'm going to answer that one. The question was whether there was any constancy in the magnetic field. How much can you assume about the magnetic field? The fact of the matter is not a whole lot, because we don't measure the magnetic field routinely in this region. We only measure it down here. And it turns out it's really hard to scale higher up in the atmosphere what the magnetic field is doing. However, so this simple model that we've discussed, that it has flaws, it's very limited, but it kind of gives you some idea of how rain happens in the sun. It's a process of heat, density rising, condensation. Condensation in this sense is not water vapor turning into liquid, but rather hot material that's condensing and creating more density. It's still hot. It's still gas. It's not water. So you have this cycle of creating those dense loops. You create something that gets gravitationally unstable and it falls down. And this explains a lot of the phenomena that we were looking at. So whenever that heating rate gets too low for the radiative cooling to be equalized, when the radiation takes over, you all of a sudden can create something out of nowhere. So that's where all of a sudden at the very loop top, you can see this material forming, and then it falls along this magnetic field. Yes? This is primarily what we'd call an active region phenomenon. So it's linked to the presence of magnetic concentrations of sunspots and other magnetic activity. And those don't cover the entire sun, but rather are patchy across the sun. The magnetic field changes configuration, so it will change as the magnetic field changes. Yeah. Okay, so we covered this earlier. The fact that the heating kind of tells you, or the way you play with this model can kind of tell you what's going on with the heating of the sun in the corona. At least gives you some constraints. However, as we've discussed, this is a very simple, idealized model, and in fact, coronal rain is much more complicated. And this is a beautiful movie from the Swedish Solar Telescope. I forget which. This is 2009. This is an instrument called CRISP, and this is quite an involved movie to explain, because what actually is happening here is you're not looking at the same piece of the solar spectrum in every frame. But instead, if you have a spectral line, for example, if you look at the rainbow of the sun, the spectrum of the sun, there's dark lines in that sun in that spectrum that correspond to particular atoms, and those have a line. So if this is the rainbow, you have a dip of a line. What this movie is doing is it's progressively, at the very beginning of this movie, it samples only this piece of the spectrum, and then it slowly goes into this line and out. So right there, you're actually here, and then as it goes in, you're further down. Doppler shifts allow this thing to change, so anything that you see at the beginning of this movie and at the end of the movie is velocities. Velocities happening towards and away from you. So this stuff here is the rain. And each red and blue dot tells you whether it's moving towards you or away from you. Red shift, blue shift. And someone actually went in and by hand traced every single piece of those. and so each dot corresponds to one parcel that he found. So what you see is something that's really not this simple 1D loop, not a simple thing happening in one spot and draining out. But you see things happening here and there that are coupled. Different pieces of the are evolving together. You can see that it's kind of gentle. It's a shower. It's not a downpour. Not always. So it kind of just gives you a little inkling at the complexity here. So there's a lot of open questions about what rain does, how rain evolves, and what creates it. The question of what that heating mechanism is still the biggest, the coronal heating problem. We don't know what it is. Another thing is that oftentimes if you measure the temperature along these loops, the temperature diagnostics that we have tell us that the temperatures are actually pretty uniform along the loop. But these models oftentimes have a hard time recreating that. You actually get a temperature gradient along it. So that's trying to tell us something, and we have to just make our models a little bit more advanced in order to try to understand that aspect of loops simultaneously with this rain. We talked a little bit about partial ionization, the neutrals and the ions, how that changes things. It changes things not only about like how that neutral material can slip across the magnetic field, but it actually changes the heating itself. So the heating, whatever's heating this loop, if it's waves, for example, those waves have to lend its energy to the gas in that loop. And whether that gas is neutral and made up of neutrals and ions, or if that gas is made up of only ions, really changes how fast that heating happens. So that's a really a big problem in solar physics right now. That one I don't think I can quote you an actual number, but I don't actually know the answer to that one. I've seen cases where visually they look the same, but I've never measured it myself, so I don't know. The other thing interesting is that in this movie in particular, someone has gone in there and quantified exactly how much mass is coming down. And he's tried to link this with, he's a Paraguay guy. Someone from Paraguay, what's the name? Paraguayan. Anyhow, he has measured how much mass is coming down out of corona, and he's linked it to how much mass he thinks is being shot up. And those spicules can be used as an estimate. And it turns out it doesn't match. There's more mass, he thinks, going up than is coming down. So there's some missing mass. We don't know where that is yet. Absolutely. So, right. So every particle sees the same gravitational field, right? A feather falls as fast as a oh, sorry. Repeat the question. The question was, can you think about the sun as having an atmosphere, and whether you can say anything about how that atmosphere is stratified with chemicals? Can it be an oxygen level? Can it be a hydrogen level, etc.? All material sees the same gravitational field. A feather goes at the same rate as a bowling ball in vacuum, right? The only way you get that stratification is through other processes. In the Earth, it's the UV and the dynamics of the weather that create stratification. In the sun, that kind of stratification can be built. However, at this point, we don't have the fine enough tools to measure that right now. So oftentimes we assume that the helium and the hydrogen abundances are the same in the corona as it is below, whereas in fact it's probably not the case. It's going to change a little bit. But great question. Okay, so I promised 3 slides. I was getting to your question about magnetic fields. So if we advance our models even more, we can move from this one into more dimensions. And this is Xi Feng, who has started to do multidimensional modeling of rain. And this is a movie that's showing you some loops created by a magnetic field, and the dark stuff is showing you regions of higher density. So when this plays at the very beginning, I want you to look at something forms here, but then something forms also right after it there. So in the model itself, it's saying that this magnetic field is coupling the dynamics and the evolution across itself. In fact, he stipulates that this is likely the fact that a small pressure difference in one piece of the magnetic arc can create an effect at the other side of that arc. So a little pressure difference will create a wave and a response that'll change the density somewhere else. So you can create rain by this perturbation, this wave in the magnetic field, and you don't actually have to turn the fire off below. This is an added complication, but more likely to be more real or more indicative of what's actually going on in the sun. But the question over here was completely right. How do we measure, how do we know what the magnetic field does? Because in fact, actually that wave of pressure, when this density, when this blob forms and this wave creates another form somewhere else, is really dependent upon how strong the magnetic field is. Because if the field is infinitely strong, it takes a lot of material to flex it. In fact, because of how numerical simulations are created, the magnetic field loop is something about 10 Gauss. We measure magnetic field in Gauss units. The magnetic field that you're sitting in this room is about a third of a Gauss. This is only 10 times larger than that. Whereas, in fact, it's actually 1,000 times stronger than that. So the simulation itself doesn't match the reality. So to get at the magnetic field is a really hard thing. The heating, the cooling, all of this spine scale dynamics, everything more complicated than that simple 1D loop is tied to a magnetic field. Whether the neutrals and the ions can be treated as one is tied to the magnetic field and tied to the densities. We'd like to get at measuring them, but that is actually really hard. And there's been a lot of work to measure magnetic fields, particularly at the surface of the sun, using polarimetry over the last 2 decades. And the last 2 decades have really, you've seen a rise in the level of instrumentation and the level of the theory behind how one might measure a magnetic field of the sun. The tool that we use most often and the most powerful for us is polarized spectroscopy. So we're doing the same thing we're looking at spectral lines, we're looking at lines of helium and hydrogen. But instead of only looking at how much light they give you, we're looking at how that light is directed in space. Light is a wave, and that wave can be angled in certain directions. It can be polarized. So the same way, anytime light reflects off of something near us on the Earth, whether that be off of the surface of the water, looking at a river, or off of a car hood, you get a glint, you get a glare that comes at you. Because of that reflection, it's polarized, and then that's why you wear polarized sunglasses, because it filters out that polarization. So we do the same thing. We look at the polarization coming from the sun, and that polarization can tell us a lot about the magnetic field. To get at coronal rain, I've done some work using the telescope that the National Solar Observatory has right now in New Mexico, and that's the Dunn Solar Telescope that's down by White Sands in right in the Sacramento Mountains above Alamogordo. Its aperture is only 76 centimeters, less than a meter. Small telescope, but huge. The one was the largest for a long time, or the most highly resolving one in the U.S. for a long time because of its adaptive optics. And what we've done there is we've looked at this rain forming in the atmosphere on the disk, and we've done this polarized spectroscopy. And I've made a map of this, and what this is actually that polarized map. So this spectrum is coming from along this stuff that's falling out of the atmosphere. And what it shows you is, in fact, there's a lot of lines here. This one here is silicon gas. This is helium gas. This is actually water vapor that's in our Earth's atmosphere. These are some calcium lines. This thing here is also helium gas, and this is that Doppler shift, that same Doppler shift. So up here it has a small Doppler shift, but then it accelerates up to 200 kilometers a second, or about 450,000 miles per hour. In the polarized spectrum, you can see that it has a weak. You don't see much where this is here, but as you get lower down, you can see it strengthens. This is telling you something about how the magnetic field is changing with height, how the intensity is changing with height. However, the big trick here is that this is methods that I was working on in graduate school, but the problem is when you're looking at a loop like that, you don't actually know how high you're looking at, because you're looking at it 2D projected, right? You don't. If I'm looking at this loop, can you tell me how tall that thing is? You don't. Turns out I was lucky, and we had 3 spacecraft at the same time going on around the Earth, around the sun, and giving us 3D views of the sun. So this is actually not that particular day, but it was about a year later. But it shows you how we get 3D images of the sun. This is the Solar Dynamics Observatory that represents Earth, from Earth. And then there's two other spacecraft called Stereo A and Stereo B, one on each side. And it's showing you a piece of the sun, and you're seeing the whole sun at once. And it turns out, actually, about 22 months ago, Stereo B, as it was going behind the sun, we lost radio contact with it because it went behind the sun. But then as it was supposed to come back, we didn't find it again. We lost it. But this week we found it. That was the big news this week. If you saw anything that says Stereo spacecraft was found. It took us 2 years, but they were pointing the Deep Space Network, NASA's Deep Space Network, at it routinely. I forget how often, but they found it in orbit finally, and they're trying to recover it now so that we're getting these 3D images again. So for me, that loop, that stuff that was raining out, this is that from Earth again, where stuff appears out of nowhere. This is what it looks like from a spacecraft that is 110 degrees in front of us in the orbit. So this is the sun, this is the Earth, the sun here. I'm using this spacecraft to look at that way. So that's happening at the same time as this. This loop comes down, and you can see here in a second this loop come down. So now I have polarimetry, I have spectra, I have height information, I have 3D, I have everything. Question? Sure. Yeah. So this is actually the same region as this little white square. So you're looking at the same thing. This gas that you're seeing here is 1,000,000 degrees. This sunspot that you're seeing is 6,000 degrees, much lower. This is on the surface of the sun. It's a concentration of magnetic field. So the magnetic field out here is fairly weak, hundreds of Gauss. Here you're looking at 3,000 Gauss or so. So this is where it's most concentrated, and these lines represent this stuff that's falling out that I've traced. Sunspots is right, yeah. So coming towards the end here, this is the most science-y slide I have in the sense that it's a lot of information and we're not going to get through it. But if you look at those polarized spectrum and you do a full analysis of the spectroscopy of how the polarization is formed, which in this case is kind of involved, you can start to measure how intense the magnetic field is along that loop. So this plot up on the left actually tells you how strong the magnetic field is along that loop. So this is within height, so I know the height because of the 3D view. So at lower heights, you get a very strong magnetic field. It goes up to 2,000 or 3,000 Gauss. And it very quickly goes down, but actually not as quickly as some models would suggest. What this allows me to do is actually tell you how bad the models are at predicting what the field intensity is. These plots on the right just tell you that I actually can give you the vector field of the magnetic field along that loop. So this black line here and here tells you in 3D space what is the trajectory of the loop. And these dots tell you what my polarized spectrum tells me it is. And there's some crazy ambiguities where the polarized spectrum will tell you it's either this way or that way. It's not this way, but it's one of those. And that's the reason for this. But the point is that I measure the full 3D magnetic field, and it matches very well with what you predict. This is the only method that I know of magnetic fields in coronal rain. Right. Right. That's a loaded existential question for a Friday. You know, it's been a long week. No, the question very delicately was basically, why do I exist and what am I here for? No, it was a very fair question. It is, what's the bigger picture here? What does this help us do? For me, it's multiple angles that this measurement gets at. One, it helps constrain models that are unconstrained. There's a lot of modelers out there doing things that are not grounded in real physics. So I'm trying to tell them what's going on and help them. Of course, they help me by telling me what's going on because I don't understand what's going on or what I'm even measuring. However, what's really important about this measurement is that this rain is in the corona quite often. And if we can measure those magnetic fields frequently and often, we can see how they change with time. And as they change with time, and as the field energy can be built up as things are churning, that's when explosion's going to happen. So that big explosion I showed you at the very beginning where the cloud was lifting off, that's a big release of twisted magnetic energy that we don't really have a good measurement for. So I'm doing two things here. I'm trying to understand the rain, but I'm also trying to understand energy and how it builds up in the sun. And the point of that is that this is weather modeling. We're trying to do space weather. We're trying to understand how the sun erupts and how does it create energy that is harmful to Earth. So if we can measure loops like this and we can perfect these techniques, we can perhaps tell you, yes, there's a big cloud of gas coming your way in about 6 hours. Maybe you should turn off your GPS satellite. Or if you have a tractor in a field that's going along a straight line because the GPS is telling it to, you should maybe turn off that tractor because the storm is going to come in and all of a sudden your tractor is going to head for the city. Or maybe flights that are going over the poles in the northern latitudes should divert because all of a sudden auroras are going to happen and high energy particles are going to happen. That's the big picture. I don't do that. I measure magnetic fields in the sun, but I hope that it's a small piece useful to somebody. This is a long-term view, I think. Yeah, Bob. Absolutely, and some you can measure those fields, how they strain at the ground layer, at the photosphere level, and try to determine when it's going to come towards us. But actually, because of this complicated density structure, this heating structure, it's hard to do a one-to-one correspondence, and the models are not perfect. There's much more to do. Yeah. Speaking of much more to do, and the other half of my job, or really the other 90% of my job, is this thing. This thing, one of the many things it's going to do is try to measure magnetic fields in the corona. I want to measure magnetic fields in the corona using this cool gas. Other people are really excited, like the people down the hall here are really excited about using it to measure magnetic fields in the hot gas. But they're complementary. This thing is 4 meters, so the 76 centimeter mirror that I was using earlier is all of a sudden expanded to 13 feet and half the size of this room, this huge thing. All of a sudden I have so much more light that I can be some 30 times more sensitive at measuring the magnetic field. This instrument is many instruments in one. The mirror, but the light of this telescope is directed down into a clean room lab that has 5 key instruments that anyone in the world can use if you propose for it. And anybody who wants to use the data can use the data. These instruments are very advanced. 2 of them are being built just down the hall by IFA. This one called Cryo-NIRSP, and this one called, which one? Oh yeah, DL-NIRSP. Here, these are the infrared ones doing a lot of the same work. They're down the labs. And there's a lot of exciting things about this project, and I could give you predictions for what we could do about coronal rain, but I think that would bore you. But the thing is exciting is that the whole world is mobilizing around this project, and it's so much bigger than just me or us or anybody. And if we can all do our small part, I think we can do some fantastic things with this. Just pictures around. I mean, this is the mirror about a year and a half ago in Tucson, actually built and ready. It's sitting in a lab, or it's sitting in a warehouse on the Air Force Base in Tucson, ready to come to us. I don't know the final schedule. The mount's going in now, so it's at least a year away. Yeah. So that's the mirror in Tucson. This is what's on the summit as of about 5 months ago. This is our crew up there. This is the base ring for that lab. So this lab here rotates throughout the day. The whole mass, all of the instruments rotate throughout the day. And this is the bearing for that and our crew there. This is our big team. I forget where this is at. This is one of our big meetings in either Tucson or Boulder. Boulder, Colorado is our headquarters. And finally, this is the freshest people. You can maybe see JD, who introduced earlier, but we're doing more and more on the island too with workforce development, because we're always needing good people. And I had the pleasure this summer of mentoring my first student. I had a great time working with the students from the University of Hawaii on some data aspects of the telescope. This is Jaron, Kari, and Joey. Joey's from Maui. I think Jaron is also from Maui, and they're up there at the telescope taking a tour. Take questions in 1 second. Let me just summarize. Clearly, rains on the sun. It's important to measure the magnetic field. It tells you a lot about how the sun gets heated. And DKIST is going to do loads to help us in this work. With that, I'll thank you and take any questions you have. Thanks. Give me 1 sec. Right. So this compared to that. Very, very different. Absolutely. So one thing to note is you're only seeing about a third of the telescope. The other 2/3 are down the ground. So this telescope is a very different design, where it has 2 mirrors on the very top that are used to track altitude and azimuth throughout the day. So it directs the sun along those 2 mirrors and directs it down straight along this telescope. And the primary mirror is actually way down 260 feet into the ground. And that actually evacuated. There's no air pipe, because if you have air in it, then as that air heats, you get turbulence. So we evacuate it to get rid of that turbulence. DKIST, however, has 40 years of engineering technology behind it to create a new design. So we can be more confident that we can control that turbulence, and we don't need the vacuum. But the other great thing is that we don't have to dig into the mountain, and that's essential. We don't want to dig any more than we have to. There would be no way we could build this telescope on Haleakala, because 260 feet of digging into Haleakala is just no way. Absolutely no way. Question here. It's quite a bit different, actually, in the sense our telescope is geared directly for looking at the sun, and because of that, there are certain challenges that we face that a nighttime telescope wouldn't face, and a lot of that is heat. So this telescope is a big air conditioner in many ways, and it's engineered around the idea of getting rid of heat and getting rid of turbulence. So there's big pipes, these black pipes show some of it, pipes of liquid about a foot wide that pull the heat away from stop, and that heat is pulled out into a separate facility where it melts ice that we generate at night. The TMT on the Big Island, it doesn't have just one mirror like this. It has 500 mirrors that are small segments put together that move. It's much bigger, but it also, you can never put it point it at the sun because there's just too much light. Yeah. Absolutely, yeah. It's losing mass because a guy named Gene Parker predicted back in the 50s it was that if you have a heated atmosphere, that heated atmosphere should lend to a wind. And then a spacecraft called Mariner 10, I think, went out and measured the fact that there's particles always being pushed out of the sun at all times. There's a wind pushing out of the sun. I don't know actually what the rate of the mass is. I could look it up. I don't have it in my head. However, that said, this mass that's being blown out in the wind is actually carving a bubble of the sun in our space. That bubble extends way past Pluto, and all of our planets are actually existing in the atmosphere of the sun. So we, in many ways, we live in the sun. And the only way we're protected from that sun is the weak magnetic field that the Earth has to help us live within a bubble within a bubble. Yeah. 4.5 billion years are okay. I don't have a lot of first-hand knowledge with the question. Sorry, the question was that there's a discussion out there that Haleakala is better for observing the sun than Mauna Kea is, and I've heard that too, and I trust it. However, I don't have first-hand knowledge of Mauna Kea in terms of how good the daytime air mass is compared to Haleakala, but the weather patterns are similar but a little different because of the height. Yeah. Right, and that helps a lot to keep dust down, right? Yeah. Okay. You fall into these things. For me, I mean, I grew up. I always. The question was how I became interested in this. How did I fall into solar astronomy? And the answer is I always liked physics. I always liked math. I liked astronomy. I sat out on the picnic table every night with my dad looking at stars. There's all of that stereotypes. However, for me, it was an opportunity that the National Science Foundation gave me as a sophomore of college to go to Montana and spend 8 weeks with a researcher in Bozeman doing solar physics. And it turned out that Bozeman is really good for hiking and rafting and fly fishing too. So half of my summer was fly fishing and rafting, and half of it was solar physics. And I thought, this ain't bad. And then 10 years later, I'm in Maui, so it's still okay. Yeah. Good question here. Right, so the question was roughly, do these arcs of magnetic fields that extend from sunspots interact on the sun? Is that very briefly? There's no such thing that we know of as a magnetic monopole. Magnetic fields are all bipoles, so there's always a plus and a minus part. So it's always connected to somewhere. Anything that comes out of the sun is connected somewhere else to either the sun or actually interstellar space, because that wind is blowing it out. But yes, as these magnetic fields come up, they do evolve with each other and can rotate around each other, depending on those convective forces in the convection zone of the sun. And if they come together in specific configurations, they can interact and release large amounts of energy in flares through something called magnetic reconnection, where one magnetic field reconnects to the other. Yeah. Question? Right. So your question is, does the loop? Oh, the question is, do these loops that we see that are hot give us any indication of why they're hot? Well, first of all, they exist, and the fact that they exist and the spectrum that they give us and the temperature that we can infer from those spectrum is why they're interesting. We know they're hot because of all of the physics and all of the observing that we've done. At that level, then we start to simulate and we start to model and we start to break it down into these 1D things, and we start to get some kind of physical intuition for why they're hot. So yes, their variation of temperature, how wide they are, how tall they get, how strong their magnetic field is, that all gives us some information about how this corona gets hot. But at this point, we don't have a consensus for why. Yeah. Absolutely, yeah. So the corona is actually a very dark piece of the sun. I mean, most of these images that I showed you, they look bright, but you're actually not seeing any of the radiation from the surface of the sun. You're only seeing hot gas. In general, the corona, the brightest it gets is some 10% as bright as the disk of the sun, and only in very specific, very weak cases. Most of the time, the stuff that we're looking at is more on 10,000ths of the brightness of the disk, or even a millionth of the brightness of the disk. So it's a dark science, and we don't have enough light. So when we get this 30 times bigger mirror, it allows us to collect that much more light. And more specifically upon Haleakala, because we have a very clean sky, very, very clean sky, it knocks down the brightness of the sky compared to the corona, so that we can see the corona in a much, much better fashion than we ever have. Yeah. The back. Sure. So the question was first about the rotation rate of the sun and how that compares to Earth, and the second was how that rotation rate of the sun affects its magnetic fields as they extend from the sun. The first, to answer your first question, you were right by the number 24, but not by the unit. It's 24 days or 25 days, not hours. So it takes about the equator of the sun takes about 25 days to go around itself, whereas the poles actually take 31 days. So it's different. So the equator of the sun rotates faster than the top of the sun. And what that does is actually as the magnetic fields sweep through space, because there's this wind that's interacting with the rotation, what you end up getting is a spiral in space. And that magnetic field, as it comes away from the sun, if you were to measure how it looks in interplanetary space, you would see a spiral. And in fact, that spiral makes an angle of about 45 degrees with Earth. And as we're orbiting the sun, we're actually directing kind of into that angle of that swept spiral of the magnetic field. Yeah. Yes. It depends on the ionization rate of the particular atom. It's easier to ionize certain ions versus other. But for the helium ion, for example, you're looking at 10,000, 20,000 range, depending on the process, whether it's radiative or if it's a collisional process that ionizes it. Yeah. Other ions, it takes much more, which is why whenever you're looking at those coronal images, the iron lines that we're looking at are iron atoms that have been ionized 12, 13 times. And the only way you can get that is by those high temperatures. It's part of the reason. Part of the reason, yeah. Right. So I think if I understand the question, it's a question of it takes. It's often said that it takes 100,000 years for the energy to propagate from the center of the sun via photons to the point that it reaches the surface of the sun and then comes towards us at Earth. How does that relate to the expulsion energy in the magnetic field? They're actually very different timescales. We know this because we look at the sun, how it evolves over years, times, and we see that the magnetic field rewraps around itself and changes directions every 11 years. So that sunspots come and go. Sunspots are, you see a lot of sunspots at one time, a few at others, and that's about how this magnetic field is generating itself in the convection zone of the sun. That's years timescale. But you're right. The energy that's created in the center of the sun by fusion, where hydrogen is burning into helium and creating extra energy into photons from its mass, because of the great density of the center of the sun, those photons, that energy bounces around in a random fashion for a long time. It takes about 100,000 years to get to the surface, and then it takes 8.5 minutes to get to us from there. Oh. At some point I should have been able to derive that, but I'd have to go back to my textbook. Well, great. I know there's other questions, but at this point, I've been going on for an hour and a half, so I wanted to take an opportunity to thank everyone for your attendance and your energy and everybody.